I'm Balu, and I'm here to introduce SilverLining. It's a data-first framework for mitigating spatial and spectral shortcuts, and it does so without introducing new confounders. This is a joint work done in collaboration with the University of Toronto, Vector Institute, and the University Health Network in Canada. Deep neural networks often exploit easy-to-learn shortcut features. Instead of learning robust features, they learn spurious associations that do not generalize. In the healthcare setting, it comes in two domains. One is in the spatial domain. These shortcuts tend to be position-dependent artifacts, such as laterality tokens in XY. The other is in the spectral domain. These tend to be image-wide patterns like scanner-specific noises or brightness shifts. These two co-occur, and we address them in a unified frame. The most natural approach to fixing shortcuts in a data-centric fashion is to identify and remove shortcut regions. And previous works have done exactly that. However, as shown in the cases of these X-rays, these create new confounders that appear in different positions across different classes. So instead of looking at the original shortcut, it learns to exploit the space instead. In order to prevent this from happening, we need to perform the correction uniformly across the classes in a confounder-free manner. We do this using the SilverLining framework. We encode image patches from the spatial and spectral domain and identify shortcut regions by training a patch-to-image level classification. For the spectral domain, we rely on the magnitude step. The attention weights reveal the most attended patches, and using the simplicity bias principle, the highest attended patches contain the easy-to-learn shortcuts. We then compute the union across these patches and correct them uniformly. The output is confounder-free data that can be used with any architecture and tasks, such as detection. The GradCam visualizations also validate this approach. ERM and masking methods fixate on the laterality token, while the model trained on data from SilverLining actually looks at the lung regions. We evaluate this in a controlled manner with a pneumonia classification task, where we measure the performance with the shortcuts reversed. We look at algorithms which use augmentation, additional losses, architecture changes, and database ways for shortcut mitigation for comparison. We see that most of the methods still learn the shortcut in varying degrees, which cause them to fail when shortcuts are inverted. SilverLining achieves a strong performance when spatial, spectral, or a combination of these two are in play. We also evaluate cross-hospital generalization by training on the mimic chest X-ray dataset and generalizing it to CheckSpread. SilverLining shows a good performance in comparison to the closest performer, which is just train twice, or JTT. We use automated shortcut labels obtained from Ong Li et al., so that manual annotation for shortcuts is not necessary. In the spectral setting, we see that class-correlated brightness confounders are correctly identified. The attention maps focus more on the DC component, which encodes the global intensity. The histogram post-correction for the pneumonia class show that the pixel intensity shortcuts is removed and the histogram is evened out. Unlike the spatial correction, we do not mask out frequency components, which would result in artifacts in the image. Instead, we blend the shortcut frequency components with non-shortcut reference images. SilverLining also extends well to other tasks, such as object detection. In this polyp dataset, there is a spurious negative association between polyps and the green boxes. The model learns to suppress detection when the green overlays are present. Law-space methods such as group DRO, which were designed with classification in mind, fail to converge in this detection setting because of the complex interplay of the losses in this new set. Because we operate on the data directly, we sidestep these issues completely. We do have more interesting details in the paper and supplementary. Please take a closer look if you found this interesting. I look forward to seeing everyone at the conference. Thank you for your attention.